For my final project, I decided to do the optimization of click-to-cast fill time. The scenario in this case is click-to-cast uses user-defined inlet locations for die casting or sand casting. There is no way to know what will be the best inlet location for a minimal amount of time unless you run multiple different tests, which isn't practical. The solution for this would probably use a code to use interchangeable parameters to find the optimum inlet location. A quick little background on what click-to-cast is. Like I said, it's a casting simulation program from Altair University that allows you to do die casting or sand casting or a couple other casting simulations. The program allows that the user input a desired geometry and select an inlet location to inject material into the mold of that geometry. The image to the left, you can see that it's a simple geometry. The red little circle, the red little square is the inlet injection, and you can define that as either a square or a circle and then mesh your material to get the simulation started. The next parameters that a user would define would be the direction of gravity, the material that they want the mold to be made out of, the injection material, and either the time to fill or the velocity to inject into that material. Then click-to-cast will give you a full simulation of the velocity going into the material and the time that it took to completely fill it. In this simulation, you can see the velocity distribution for the simple cube that I decided to pick. I wanted to do an initial test to sort of get a reference of how click-to-cast would work. Now here you can see the time distribution of how long it would take to fill up this certain mold. As you can see, it's not very uniform and it has a lot of different hotspots. So a model summary of this project was originally I was thinking of running an unconstrained optimization MATLAB code to get one specific value for the inlet location. After further learning in this class, I realized that a generic algorithm would be much better suited for this analysis, mainly the reason being that I can run multiple iterations to find a mean value and a best value based on that inlet location. So I first decided that I wanted to come up with a simple cube-shaped geometry. For this reason is because it has a nice flat edge that I can use a square inlet and have very easy to find location for that inlet, and it will give me much easier constrained values. The second step in this process was I ran a simulation to sort of gain that perspective of how a cast was going to work and what was going to look like when the material was injected into the mold. For that, I had to then come up with an equation based off of how I believed the injection was taking place. This equation would take into effect forces acting on the liquid in the cube, the forces acting on the inlet, and the velocity that the liquid has from the inlet. This would mean a manipulation of gravity, hydrostatic pressure, and velocity. The third step, the constraints would need to be defined based on the geometry of the inlet and the geometry of the mold. I made the dimensions of the cube to be very simple, like 12 inches by 12 inch by 12 inch, the inlet to be a 1 inch by 1 inch square. So the fitness function would be defined based on the equation created in step 2, and the upper and lower bounds set by the middle of the inlet to the edge and along each axis. What I found from my results is when I ran the simulation the first time, at the top, I got a fill time of about 1.3 seconds. This seemed reasonable because it was a small cube and it had a really fast inlet velocity. Now the generic algorithm gave me an inlet location of the exact opposite, the bottom center of the cube. I was skeptical at first, mainly because of hydrostatic pressures, the gravity, everything acting on that inlet location. I didn't think that would actually give an optimum output. But as I found that when I ran this, the time was found to be 1.2 seconds. Now this is not as big a jump as the original casting mode, but it did give me a much quicker value. So here you can now see the simulation inlet time. It's much more consistent and smooth, and there's a lot less hotspots. And here's the simulation of the inlet velocities. As you can also see, it's a lot more smooth and a lot more consistent. Some continued work I'd like to do after this is more complicated geometries to be able to allow any user to put their input geometry in there and find the optimum inlet location to decrease the amount of time for filling. The next step would maybe do an optimum fill speed for a set time, and then the third step would be to do an optimum fill distribution. Unfortunately, in click-to-cast, it doesn't give you a perfect fill distribution. It sort of makes sense, but I would love to eventually do an optimization that gives you the best fill distribution for your inlet location. here are a couple of references, how I came up with my equation, and a little bit of learning about it. Any questions?